Hello! In this video, we are going to prove the following theorem. Suppose a, b, and c are integers. If a squared plus b squared equals c squared, then 60 is a divisor of abc. So what we're essentially proving here is every product of Pythagorean triples is a multiple of 60. So for example, 3, 4, 5 is a Pythagorean triple, and so are all of these guys. But it turns out, if you perform 3 times 4 times 5, that's a multiple of 60. 5 times 12 times 13 is a multiple of 60. 8 times 15 times 17 is a multiple of 60, and so on and so forth. Now, to prove this theorem, we're going to use modular arithmetic. And we're going to use the following definition. Suppose a and n are integers where n is greater than 0. We denote a mod n to be the remainder of the division problem a divided by n. Now, some properties of modular arithmetic we are going to use are the following. If a mod n is equal to a prime and b mod n is equal to b prime, then it turns out a plus b mod n is equal to a prime plus b prime mod n. Also, ab mod n is equal to a prime b prime mod n. Okay, so now let's get into proving this theorem. To start out the proof, let's give ourselves 3 integers a, b, and c, where a squared plus b squared is equal to c squared. The whole goal from here is to show that 60 is a divisor of ABC. And to show that 60 is a divisor of ABC, it suffices to show that 3 is a divisor of ABC, 4 is a divisor of ABC, and 5 is a divisor of ABC. Now first, let me just explain why showing these 3 things implies that 60 divides ABC. Well, if we know that 3 divides ABC and 4 divides ABC, it follows that the product 3 times 4 divides ABC. In other words, 12 divides ABC. The reason why that works is because the greatest common divisor of 3 and 4 is 1. Similarly, if we also know that 5 divides ABC, and we also know 12 divides ABC, well then the product 5 times 12 must divide ABC. Because the greatest common divisor of 5 and 12 is 1. And therefore 60 divides ABC. Now, this property that one integer divides ABC and another integer divides ABC implies their product divides ABC, because their greatest common divisor is 1, has a proof that I'll link down in the description below. So yeah, this is the reason why showing these 3 things is enough to say that 60 divides ABC. So let's start out by showing 3 divides ABC. It turns out, to show 3 divides ABC, it suffices to show that a squared mod 3 is equal to 0, b squared mod 3 is equal to 0, or c squared mod 3 is equal to 0. So why is it showing at least one of these 3 equals 0 enough to show 3 divides ABC? Well, it has to do with this fact regarding modular arithmetic. Given any integer a, if a squared mod 3 equals 0, then a mod 3 equals 0. And it turns out, any integer squared mod 3 is equal to 0 or 1. So then, why is this true? Well, given any integer a, we have a mod 3 equals 0, 1, or 2. But in each of these cases, what is a squared mod 3 going to be? Well, if a mod 3 equals 0, then by our second property, regarding modular arithmetic, it follows that a squared mod 3 equals 0 squared mod 3, which is equal to 0. If a mod 3 equals 1, then a squared mod 3 is equal to 1 squared mod 3, which is equal to 1. If a mod 3 equals 2, then a squared mod 3 is equal to 2 squared mod 3, which is equal to 4 mod 3, and that's equal to 1. So we see, no matter which case we have, a squared mod 3 is equal to 0 or 1, which is exactly what we stated. But why is this implication true? Well, the reason why is because we have precisely shown that the contrapositive is true. That is, if a mod 3 is not equal to 0, then a squared mod 3 is not equal to 0. Right? We see in each of the two cases where a mod 3 is not equal to 0, a squared mod 3 is not equal to 0. Therefore, this implication is true. So, why does this implication tell us that to show 3 divides ABC, it suffices to show one of these 3 is equal to 0? Well, if we've shown that one of these 3 are equal to 0, well, let's say that we've shown a squared mod 3 is equal to 0. By this implication, a mod 3 is equal to 0, which means 3 is a divisor of a, and therefore 3 is a divisor of ABC. Right? That's the reason why it suffices to show one of these 3 is true. Okay, now going back to our proof, let's take this equation and mod 3 both sides. If we do that, left-hand side is going to be a squared plus b squared mod 3 equal to the right-hand side, which is c squared mod 3. Now, on the left-hand side, we can apply our first property regarding modular arithmetic, which tells us that the left-hand side is a squared mod 3 plus b squared mod 3, the entire thing mod 3. Now, the goal is to show that at least one of these 3 is equal to 0. Now, if a squared mod 3 or b squared mod 3 is equal to 0, then we're done. So let's suppose that this is not the case. Well, if that's not the case, then a squared mod 3 is not equal to 0, and b squared mod 3 is not equal to 0. Well, we know that any integer squared mod 3 is equal to 0 or 1, so in this case, we have that a squared mod 3 is equal to 1, and b squared mod 3 is equal to 1. Well, if we take these two guys and plug them into our equation, we're going to get 1 plus 1 mod 3 is equal to c squared mod 3. And 1 plus 1 is just 2, so we get 2 mod 3, which is equal to 2. But c squared mod 3 is equal to 0 or 1. But that's absurd. So we've reached a contradiction. So overall, what have we shown here? Well, we considered two cases. One case was, well, if a squared mod 3 equals 0 or b squared mod 3 equals 0, we're done, because at least one of these 3 guys is equal to 0. The other possibility was that that's not the case. Well, if that's not the case, we get a contradiction. So, what we've shown here is that it is always the case that a squared mod 3 equals 0 or b squared mod 3 equals 0. And therefore, at least one of these guys is always equal to 0, which means 3 divides ABC. So we've shown 3 divides ABC, now let's show 4 divides ABC. Now, to show 4 divides ABC, it turns out it suffices to show that a squared mod 8 equals 0, b squared mod 8 equals 0, or c squared mod 8 equals 0. And the reason why has to do with this result regarding modular arithmetic. Given any integer a, if a squared mod 8 equals 0, then a mod 4 equals 0. It turns out, any integer squared mod 8 is equal to 0, 1, or 4. So, why is this true? Well, given any integer a, A mod 8 is equal to either 0, 1, 2, 3, 4, 5, 6, or 7. In each of these 8 cases, what is a squared mod 8 going to be? Well, I'll leave out the details, but in each case, we're going to get 0, 1, 4, 1, 0, 1, 4, 1. So we see no matter which case we have, a squared mod 8 is equal to 0, 1, or 4, as we stated. But why is this implication true? Well, to start, it turns out if a squared mod 8 is equal to 0, then a mod 8 is equal to either 0 or 4. So then why is this true, according to what we have here? Well, the reason why this is true is justified by the contrapositive, right? If a mod 8 is not equal to 0 and not equal to 4, then we have either this, this, or this is true, or this, or this is true. Well, we see in each of these 3 cases, a squared mod 8 is not equal to 0. In each of these 3 cases, a squared mod 8 is not equal to 0. So, yeah, the contrapositive is true, therefore this implication is true. And then it turns out, in each of these 2 cases, if a mod 8 is equal to 0, then a mod 4 is equal to 0. If a mod 8 is equal to 4, then a mod 4 is equal to 0. The reason why is because if a mod 8 is equal to 0, this means 8 divides a. So, of course, 4 divides a, and therefore a mod 4 is equal to 0. So then what happens if a mod 8 is equal to 4? Well, if a mod 8 is equal to 4, this means that a is an integer of the form 8k plus 4, for some integer k. But then we can factor out a 4, so a is equal to 4 times some integer, which tells us 4 divides a, and therefore a mod 4 is equal to 0. So we have shown that this implication is true. But why does this fact tell us that to show 4 divides ABC, it suffices to show that at least one of these guys is equal to 0? Well, if one of these guys is equal to 0, let's say a squared mod 8 is equal to 0. Well then, by this fact, it follows that a mod 4 is equal to 0, and therefore 4 divides a, and therefore 4 divides a BC. So yeah, that's the reason why it suffices to show at least one of these guys is equal to 0. Going back to our proof, let's take this equation and mod 8 both sides. Similar to what we did in the previous paragraph, we're going to get a squared mod 8 plus b squared mod 8, the entire thing mod 8, equal to c squared mod 8. If a squared mod 8 or b squared mod 8 is equal to 0, then we're done. So, let's suppose that this is not the case. Well, then we have that a squared mod 8 is not equal to 0 and b squared mod 8 is not equal to 0. Well, we know that a squared mod 8 is equal to 0, 1, or 4, so the only 2 possibilities we're left with is that a squared mod 8 is equal to 1 or 4. Similarly, b squared mod 8 is equal to 1 or 4. So this gives us a total of 4 possibilities. Either they're both equal to 1, both equal to 4, this one's equal to 1, this one's equal to 4, this one's equal to 4, this one's equal to 1. And we're going to consider all 4 of those cases. What we're going to see is that some of those cases will lead us to a contradiction. So that tells us that those cases are impossible. In all the other cases, we're going to discover that c squared mod 8 is equal to 0. So let's start with the case where both these guys are equal to 1. Well, if this is true, well then if we substitute this into our equation, we get 1 plus 1 mod 8 equals c squared mod 8. Now, 1 plus 1 mod 8 is just equal to 2, and c squared mod 8, as we know, is equal to 0, 1, or 4. So what we see here is 2 is equal to 0, 1, or 4, which is absurd. So in this case, we get a contradiction. So this case is impossible. Now let's move on to the case where they're both equal to 4. Well then, plugging this into our equation, we get 4 plus 4 mod 8 equals c squared mod 8. Now, on the left-hand side, we have 8 mod 8, and 8 mod 8 is just equal to 0. So this tells us c squared mod 8 is equal to 0. I just realized I wrote case 4, this is case 2. So this completes case 2. Now let's move on to case 3, where this guy is equal to 1, this guy is equal to 4. Well, if we take this and substitute it into our equation, we get 1 plus 4 mod 8 equals c squared mod 8. Now, 1 plus 4 mod 8 is equal to 5, and c squared mod 8 is equal to 0, 1, or 4. So we see that 5 is equal to 0, 1, or 4, which is absurd. So in this case, we get a contradiction, so this case is impossible. Let's move on to our final case, where this guy is equal to 4, and this guy is equal to 1. Well, it turns out we get a similar argument as case 3, we get a contradiction. So this case is impossible. So we've considered all 4 cases. And now let's put this all together. What we've done here is we noticed 2 possibilities. If a squared mod 8 equals 0 or b squared mod 8 equals 0, we are done because at least one of these guys is equal to 0. In the other possibility, that's not the case. And in that situation, we considered 4 cases. Only one of them was possible. And in that case, c squared mod 8 is equal to 0. So at least one of these guys is equal to 0, no matter what. And as we said before, this is enough to show 4 divides ABC. So now, all that's left to show is that 5 divides ABC. Now to show 5 divides ABC, it suffices to show a squared mod 5 equals 0, b squared mod 5 equals 0, or c squared mod 5 equals 0. Why to show this? It's enough to show that at least one of these 3 is equal to 0. Well, it has to do with this fact regarding modular arithmetic. Given any integer a, if a squared mod 5 equals 0, then a mod 5 equals 0. And also, it turns out any integer squared mod 5 is equal to 0, 1, or 4. And I don't usually do this in videos, but I'll leave it up to you guys to show that this is true, right? It's really similar to the result that we looked at for mod 3 and mod 8. But in any case, why does this fact tell us that it is enough to show that at least one of these guys is equal to 0, to show that 5 divides ABC? Well, if one of these guys is equal to 0, let's say a squared mod 5 is equal to 0. Well then, this fact tells us that a mod 5 is equal to 0, which means 5 divides a, and therefore 5 divides ABC. Okay, now to start, let's take mod 5 on both sides of this equation. If we do that, we are going to get a squared mod 5 plus b squared mod 5, the entire thing mod 5, is equal to c squared mod 5. Now, if a squared mod 5 equals 0 or b squared mod 5 equals 0, then we're done. So let's suppose that this is not the case. Well, if this is not the case, then a squared mod 5 is not equal to 0, and b squared mod 5 is not equal to 0. Well, we know that a squared mod 5 is equal to 0, 1, or 4, so in that case, we must have a squared mod 5 equal to 1 or 4. Similarly, if b squared mod 5 is not equal to 0, we must have that b squared mod 5 is equal to 1 or 4. So this gives us a total of 4 cases. either they're both equal to 1, they're both equal to 4, this one's equal to 1, this one's equal to 4, this one's equal to 4, this one's equal to 1. And we are going to consider all 4 cases. Some of these cases might lead us to a contradiction, and that means that that case is impossible. In the other cases, we're going to see that c squared mod 5 is equal to 0. So, let's start out by considering the case where they're both equal to 1. Well, if we take this and substitute that into our equation, we get 1 plus 1 mod 5 equals c squared mod 5. Well, we know that this is just going to be equal to 2, but c squared mod 5 is equal to 0, 1, or 4, which contradicts the fact that it's equal to 2. So we've shown that this case is impossible. So now let's move on to our next case, where they're both equal to 4. Well, if we take this and substitute it into our equation, we get 4 plus 4 mod 5 equals c squared mod 5. Notice on the left-hand side we have 8 mod 5, which is equal to 3. But c squared mod 5 is equal to 0, 1, or 4, which contradicts the fact that it's equal to 3. So we have shown that this case is impossible. Now, let's consider the case where this guy is equal to 1 and this guy is equal to 4. Well, if we plug this into our equation, we get 1 plus 4 mod 5 equals c squared mod 5. But the left-hand side is just 5 mod 5, and that's equal to 0. So we've shown that c squared mod 5 is equal to 0. So now let's move on to our next case, where this guy is equal to 4 and this guy is equal to 1. Well, it turns out this case is similar to case 3. We're going to see that c squared mod 5 is equal to 0. So, let's put this all together now. We considered 2 possibilities overall. The first possibility was, well, if a squared mod 5 equals 0 or b squared mod 5 equals 0, then we're done. Because that means one of these 3 are equal to 0. The other possibility is that it's instead false. And so from there we discovered 4 cases to consider. Well, it turns out only 2 of those cases were possible, and in each of those 2 cases, c squared mod 5 is equal to 0. And therefore, at least one of these 3 is always 0, no matter what. And this was enough to show that 5 divides ABC. And because we've shown all 3 of these things are true, from the discussion we had at the beginning of this video, this was enough to show 60 divides ABC. So this completes the proof. And so yeah, that's pretty much it for this video.